Hello, everybody. Today we are going to be doing a little short unit for today and next class on chapter 11 in the textbook, which we skipped ahead past that chapter to do unit 12. But now we're going to go back and do a couple lessons in this, and these are going to be the last two lessons of new material for the entire school year. So after these two lessons, we're going to spend the rest of the time just reviewing for the AP test, which is in about a month. All right, so on the top of the note sheet here, we got our objective. So we'll be learning how to find the expected counts for categorical distribution and also to do what's called a chi-squared goodness of fit test. So you got the corresponding pages in the textbook there, and then also homework problems to do from the textbook 1 through 25, odds only. Now for this discovery activity, since we can't do it in class, I found a video going through it. So there's a link on the website that you might have seen already that kind of goes through and explains the activity. So you can go through and watch that in place of this beginning section on the notes. All right, so we got some new vocab, and essentially what we're learning today in next class are two different types of significance tests that we're just adding to kind of our list of different significance tests that we can do in different situations. So what we're going to learn about today is called a chi-square test. You can see it's spelled C-H-I. So it's a little bit different. It's not chi-squared. It's called the chi-squared goodness of fit test. All right? And in a chi-squared goodness of fit test, that tests a null hypothesis that a categorical variable has a specific distribution. All right? So this is a way we can help analyze a distribution of categorical data. Something else we need to know is something called an expected count, which we talked about this a little bit in Unit 6, dealing with expected values. But the expected count would be the count drawn if the null hypothesis was true. In order to calculate that, we're going to multiply each of the null hypothesis probabilities by the sample size, which you'll see in the first example. So as we're setting up the significance test, the same format is going to stay the same as a regular significance test. We're going to start off with saying what type of test we're doing, our parameter, and we're going to list our null and alternative hypotheses. Then step number 2, we're going to check our conditions. So our conditions, very similar to ones that we've done already. So we got that random condition. Our data has to be collected randomly to reduce bias. When you have the 10% condition, it means our sample size can't be larger than 10% of the population. And then our third condition is that the large counts, for large count rules, and then for this is a little bit different for the goodness of fit, is that all expected values need to be greater than 5. And I'll talk about that more in this first example. And then we have a formula up here that you're going to need to have memorized. So make sure you have that written down on your notes. This is the formula that we're going to be using on step 3 to calculate our p-value. Then the last part, step 4, we do our analysis, decide if we're going to reject or fail to reject the null hypothesis, and then write our contextual sentence after that explaining what that means in context with the problem. So let's go on to practice number 1. So I'll read through it. A grocery store sells 4 different sizes of a popular brand of cornflakes. For the past few years, the proportion of boxes they sell of each size has been quite stable. 10% small, 15% medium, 60% large, and 15% jumbo. They decide to change the pricing of the 4 sizes and want to see if this changes the proportion of boxes they sell of each size. To test this, a few weeks after changing the prices, they take a simple random sample of 120 transactions involving cornflakes and count how many boxes of each size were sold. Here are the results. Okay, so they have this standard percentage of how many people buy these different sizes of box of cornflakes, and then they change the prices, and then this is what our observed values are. So that's our actual data. And you can see it's categorical because we have 4 different categories they could have responded into: small, medium, large, or jumbo. So what a goodness of fit test does is if we test to see if there's a difference between our categorical distribution that we got from our data, our observed values, and then what we would expect it would be our null hypothesis. Okay? So part A, it says, this whole question is kind of breaking down that all the different parts of significance test, kind of part by part. But if you saw this on a AP test, you might have to do the whole test just as like one section, like we usually do a significance test. But to help kind of get practice with this, we're just going to do this a little bit at a time. All right, so part A, we wish to carry out a significance test to see if the distribution of sizes of cereal boxes sold has changed. State the null and alternative hypotheses for this test. All right, so we're seeing if the percentages have changed since we increased the price. So when we're coming up with our null hypothesis, it's going to look different, a lot different than what we've done before. So for the null hypothesis, you're going to have to write the probability, the proportion that we'd expect for each different category. So again, the null hypothesis is a statement of no difference. So if there's no difference, then our proportion would be the same as it was before the price change. So we have 10% small. So I write that down here and kind of use this abbreviated notation. So it's the proportion of small boxes equals 0.10, proportion of medium boxes equals 0.15, proportion of large boxes equals 0.6, proportion of jumbo boxes equals 0.15. So again, if there wasn't a difference between the price change, we do expect that those different values, those would be the proportion values for each different category. Now the alternative hypothesis is that it's different than that. So what we put down for our alternative hypothesis, at least 2 proportions are incorrect. The reason that we put that down is if it's different, it doesn't necessarily mean that all 4 categories are different, right? So we're not going to put like a p is not equal to 0.10. We're not going to do that, because it could be different without all 4 categories being different. And then we don't say at least 1, because if at least 1 is different, then there's a second one that has to change, because the proportions have to add up to 1, or the probabilities have to add up to 100%. So if 1's different, then that's going to change at least one of the others. So your alternative hypotheses for all these goodness of fit tests is going to be at least 2 proportions are incorrect. And for these goodness of fit tests, it's always going to be one-sided, since we don't have a greater than or less than sign. So yeah, that's what we're going to do for our last part there. So I'm going to break up these videos a little bit to make it a little bit smaller video size. So our next video, we're going to jump on to part B.